We'll consider the Eisenstein's criterion for irreducibility of a polynomial. The statement is let R be a unique factorization domain and consider a polynomial f of x over R such that its degree is positive, and P be irreducible element of R such that P divides AI for I equal to 0 to n minus 1. So P divides A naught, A1 and so on an minus 1, and P doesn't divide an, and P square doesn't divide A naught in R. Then we need to show that f of x is irreducible in f of x, where f is the quotient field of R. So the proof goes like this. So we are given with the polynomial f of x over R. Let us consider its content. So let us denote it by C. So C be the content of f of x. Okay. So what is content of a polynomial? It is the GCD of all the coefficients in the polynomial, right? So the content divides all the coefficients. So I can write every coefficient ai of this polynomial as content into some bi. Okay, this is for every I equals 0 to n. Now let me consider a polynomial g of x, a polynomial with coefficients these bi's. So let me write it as b naught plus b1x and so on bn x power n. It's again a polynomial over R. Okay. Then I can write for the polynomial f of x, where I have ai is equal to cbi. So I can write f of x as equal to c content of f, okay, into bi. And what is that bi? It is f of x is equal to c of f into g of x, because I have ai is equal to c into bi. Bi's are coefficients of the polynomial g of x. Okay, so once I have written f of x as its content into g of x, then this g of x polynomial is a primitive polynomial. It is a primitive polynomial. Okay, so now we are given with the irreducible element p of R, right? And C is content of the polynomial f of x. Then clearly P doesn't divide the content of f. Okay, why? Because P doesn't divide an. P doesn't divide this coefficient, right? So P doesn't divide content of f. Content of f is the GCD of these numbers a naught, a1 and so on an. Okay, so P doesn't divide C of f because P doesn't divide an by the hypothesis. Okay, but again it is given that P divides ai, right, for I from 0 to n minus 1, right? So P divides ai for I equal to 0 to n minus 1. P doesn't divide C, so it implies that P divides bi for 0 to n minus 1. So it implies that P divides bi for I equals 0 to n minus 1. Okay, again P doesn't divide an, okay, and P square doesn't divide a naught, right? So P doesn't divide an, P square doesn't divide P doesn't divide an and P square doesn't divide a naught. It implies that P doesn't divide bn and P square doesn't divide b naught. Okay, because I have f of x is equal to c into g of x here, right? So now if g of x is irreducible, if g of x is irreducible in f of x, okay, then f of x is also irreducible in f of x. Okay, now f of x is an associate of g of x in f of x, right? So it is enough if we prove the assertion that f of x is irreducible in f of x when the polynomial f of x is primitive. So we can consider only this case when f of x is primitive polynomial. It's enough if we show this for the primitive polynomial f of x. Okay, so and the Gauss lemma, according to the Gauss lemma, f of x is irreducible in f of x if and only if it is irreducible in R of x. So to prove that it is irreducible in f of x, it is enough if we show that it is irreducible in R of x. Why? I can use the Gauss lemma. These two are equivalent statements according to the Gauss lemma. Okay. So now we will prove that f of x is irreducible in R of x. We will assume the contrary part of it. What? We will assume that f of x is reducible in R of x. So contrarily, suppose f of x is reducible in R of x. Okay, then I can write f of x as equal to u of x into v of x for some u and v, the polynomials which are non-units in R of x. I can write f of x as a product of two non-units in R of x. Okay, now we will claim here that degree of both of these polynomials, u of x and degree of v of x, both are positive, both are greater than 0. Okay, now we will consider if degree of u of x is equal to 0. Suppose degree of u of x is equal to 0. Then it is an element of R because it's a polynomial over R. Okay, so then u of x is an element of R. Let me take it as a. Okay, so u of x is equal to a belonging to R. Then I can write for f of x as equal to u of x into v of x as a into v of x. Okay, now v of x, again I can write it as the content of it into the primitive polynomial. Okay, so let me take it as b. So a into b into v1 of x, where b is the content of the polynomial v of x. Okay, and what is this v1? v1 is a polynomial over R again, and it is primitive polynomial. Okay, now f of x is a primitive polynomial, v1 of x is a primitive polynomial, so it follows that a into b is a unit in R. Okay, so a into b is a unit in R, which in turn implies that a is a unit in R. So once a is a unit in R, units of R are in units in R of x, so it is a unit in R of x. Okay, now this is a contradiction. What is our a? A is nothing but u of x, so it implies that u of x is unit in R of x. But what is u of x? U of x is a non-unit in R of x, so this is a contradiction to the fact that u of x is a non-unit in R of x. So our assumption that degree of u of x is 0 is wrong. So degree of u of x must be greater than 0. Similarly, we can show that degree of v of x is also greater than 0. Okay, so both are of positive degrees. Let us take their degrees as R and S. So let me take degree of u of x is equal to R, degree of v of x is equal to s, and I have f of x is equal to u of x into v of x. So f of x is a polynomial of degree n, so I must have n is equal to r plus s. Okay, so let me consider the polynomial u of x as alpha naught plus alpha 1 x and so on alpha r x power r, and let me take v of x as equal to beta naught plus beta 1 x and so on beta s x power s. Okay, now if p divides each alpha I, okay, if p divides each alpha I, then p divides, what is our u of x? U of x is this, and f of x is equal to u into v here, right? So if p divides each alpha I, then p divides each coefficient of f of x, which is not possible because by hypothesis p doesn't divide an, right? By hypothesis what we have here, we have that p doesn't divide an. So there is some alpha I in this such that p doesn't divide alpha I. So p doesn't divide alpha I for some I. Okay, now let us consider the least suffix such that p doesn't divide alpha I. So let me take it as k. So k be the smallest suffix, okay, such that p doesn't divide alpha I. Now by hypothesis what do we have? P doesn't divide, p square doesn't divide a naught, right? That is the hypothesis here. P square doesn't divide a naught. And what is a naught? A naught is equal to u into v. So what will be a naught? It will be alpha naught into beta naught. Okay, so P cannot divide both alpha naught and beta naught. Okay, so let us assume that it may divide one of them. It cannot divide both alpha naught and beta naught, right? So we'll assume that P divides alpha naught, P doesn't divide beta naught. Okay, so assume that P divides alpha naught but P doesn't divide beta naught here. Let me just mark it as the statement 1 here. Okay, now consider this statement f of x is equal to u of x into v of x. Okay, and let us equate the coefficients of x power k on both sides. Okay, so what is the coefficient of x power k on the left hand side for f of x? It is ak. And what is the coefficient of x power k in the product u of x v of x? It is alpha k beta naught plus alpha k minus 1 beta 1 and so on alpha t beta k minus t. Okay, let me consider this as the second statement where this t plus k, okay, it is equal to s. Now by our choice of k, that k is the smallest suffix such that p doesn't divide alpha k. Okay, so by the choice of k, p divides alpha I for every I between 0 to k minus 1, right? I between 0 to k minus 1. So p divides alpha k minus 1, p divides alpha k minus 2 and so on, p divides alpha t here, right? So p divides this part, right? Now s is greater than 0, right? The degree of v of x is positive, so s is greater than 0. So r is strictly less than n and also k is less than or equal to r here, because k is the smallest suffix such that p doesn't divide alpha k, so it is less than or equal to r here. Now again by hypothesis, p divides a naught a1 and so on and so p divides ak, because p divides a naught p divides a naught a1 and so on ak n minus 1, right? And our k is less than or equal to n minus 1 because it is strictly less than n, so p divides ak here. So once p divides ak and p divides this part, we have p dividing this part here. Okay, so p divides alpha k into beta naught, right? So which implies that p divides alpha k or p divides beta naught, because p is prime, it's a irreducible element in the unique factorization domain, so it is a prime element here. So p divides alpha k or p divides beta naught, which is a contradiction to the fact that p doesn't divide alpha k and p doesn't divide beta naught. Okay, so p doesn't divide alpha naught, p doesn't divide beta naught, right? So p doesn't divide alpha k, p doesn't divide beta naught, right? So we have a contradiction here. So now fine. So it happened because of our wrong assumption. What was the assumption here we made? We made that f of x is reducible in r of x. Okay, so our assumption is wrong. So f of x must be irreducible in r of x. So by Gauss lemma, we can say that f of x is irreducible in f of x also.